In today's lesson, we are going to be looking at probability distributions. So this is the first lesson in our new unit, and it is going to incorporate a little bit of everything that we've kind of looked at so far in terms of simple probability, permutations, combinations, and focusing on the probability portions of those different units. So before we get into it, let's just do a little bit of review of some of the things we've looked at so far. So again, how many ways there are for Sam to get to school? And so this is an application of combinations looking at Pascal's triangle. I'm just going to go through and quickly come up with the answer. Again, if you want, you can pause the video and try this before I come up with the answer. I'm going to quickly use the magic of technology to quickly just input the answer. And there are 175 ways to get from, or for Sam to get to school. Again, we're assuming that we're only going south and east or down and to the right based on this map. Next one, McDonald's McCafe has the following options for their drinks: 4 types of milk or cream and 2 types of sugar. How many ways could a person order a drink? So this is going to be that kind of problem solving with combinations. So we can say 2 to the power of 6 because we have 6 options, or 6 distinct items we could say. So again, the idea that there's the 4 different types of milk or cream, 2 different types of sugar. So 6 distinct items and 2 options for each, right? Either picked or selected and not picked. So 2 to the power of 6. We don't need to subtract 1 because we could have the option where we don't put any milk, cream, or sugar into our drink, right? And just have it plain or black. So with our probability distribution, there's some key terms that we want to think about or want to learn about or know or just refresh our memory of. So a probability distribution, which is going to be the main concept for this unit, a probability distribution lists the probability of each possible value of the random variable. So the probability distribution is a list of all the probabilities of all the possible values. Now it's often shown as a graph of probability versus the value. So we will be seeing graphs of probability versus the value or the outcome. Specifically, when we talk about random variables, the random variable is a quantity that can give a range of values. So it's going to be the range of possible values for our situation. Usually it's designated by a capital letter X, and then the individual values, so all the different possible values within that variable, are designated by a lowercase x. Discrete variable and continuous variable. So these are 2 things of what our random variable could be. A discrete variable, they're obtained by counting. So this means there are only certain values that the inputs can be, or there's only certain values that our random variable could be. Continuous variable generally is obtained by measuring. So it could be measuring time or weight or distance, things like that. And a continuous variable, there's no limitation on the input value. So there's no possible limit onto what the values could be. It could be an infinite number of possible values. So if you think of you're recording the time of something, depending on how accurate your measurement is, you could have an infinite number of possible times, right? Going down to where maybe you time something to the hour, then the minute, down to the second, down to the millisecond, microsecond, nanosecond, and even smaller than that. Right? So depending on how accurate your measurement is, you could have an unlimited amount of possible values. When we're looking at the probability distribution, the other thing that we can look at is the expected value, or what we call weighted average. So basically, this is basically predicting the average of all possible outcomes, or what we should expect to happen, right? What we can expect to happen in our scenario. So just looking at some of the terminology, this is just, again, E capital X is just our expected value. This giant letter here, this is just sigma, which means sum of. So we're finding the sum of all the x's. So this would be the values, or individuals' values of our random variable, or we could say the outcomes. And it's multiplied by the probability of each outcome. So we're basically taking the outcome multiplied by its probability and adding all of those possible outcomes up to get what is the expected value or the weighted average, or what should we expect to get. And again, we'll be looking at scenarios that kind of walks through this. So, for example, the following table gives the probability distribution of the number of digits in street addresses in a large city. So this is basically what, if you're looking at the address, how many numbers could there be on the address? 1, 2, 3, 4, or 5. So we want to think about, okay, first, what is the random variable, right? What is the variable that has a range of possible values? In this case, it is our x value, or capital X, or again, the possible values are lowercase x. So our random variable is the number of digits. So the number of digits used in street addresses. That's our random variable, and we see all the possible values for that random variable. We have 1, 2, 3, 4, or 5. Now what we want to do, we want to create a probability histogram for that, for those different values. We do have the probabilities already listed, so we can go through and create a probability histogram. We'll start off at 0, let's say 10, 20, 30, 40, 50. And we're going to look at possibility of there being one outcome, 2, say 1, 2, 3, and 4. 4 and 5. So again, a histogram does have or does contain no spaces between the bars, so we do want to be mindful of that. So looking back up, for the probability of there being 1, we have 14. So 14 would say be about here. So actually, let's move this over a bit. We'll say this is 1. We'll change these up. 2 is 31. 3 is 42. 4 is 11. And 5 is 2. So we'll just briefly shade that in a little bit just to get a look at how our probability distribution is. So again, this is a distribution that shows us how the probabilities of each outcome are spread out. And next, we want to calculate the sum of probabilities. Right, so if we go through the sum of probabilities, we start off at 1, which was 14. I'm just going to put the numbers above. So 14%. Plus, we have 31% for the next one. Plus 42. Plus 11%. plus 2%. And when we add all these probabilities up, we get that the sum is equal to 100%, which makes sense because the probability distribution lists the probabilities for all the possible outcomes. Right? So if these are all of our possible outcomes, it should all add up to 100% or 1 because that covers all of the cases. The next example, so show the or a newlywed couple plans on having 3 children. We want to show the distribution for the number of girls in the family. So we want to look at the number of possible outcomes for having the different number of girls. Right? So if we want, we can do a tree diagram to help us. So boy, girl, and then off of each one, boy, girl, boy, girl, boy, girl. So we want to think about, okay, how many possible outcomes are there? Or basically looking for the probability. So looking for 0, how many ways are there to have 0 girls? Well, starting off, we can again highlight the different pathways. So I'm only going to do one and just to kind of show. So there is one example of having no girls. So there's one, the frequency is 1. There's one of them. We could look through all the other ones, but we would find that there is no other case with no girls. So the probability is going to be 1 out of 8. There's 8 total outcomes, 1 out of 8. For one girl, again, we could go through and look at all the different outcomes or find that there are 3 outcomes where there's only one girl. So that would be 3 out of 8. For 2 girls, same thing, go through and check and you'd find that there'd be 3 out of 8 as well. And then for all girls, or 3 girls, there would be a 1 out of 8 chance. And just by looking at this, we can see that 1/8 plus 3/8 plus 3/8 plus 1/8 works out to 8 out of 8 or 100%. So that makes sense, right? Because the probability of all the cases should add up to 1 or 100%. Next, we want to create a probability distribution for this. So we're going to look at the number of girls on the bottom. This one's going to be a little bit different. So we have 0. We'll just put the fraction 1/8, 2/8, 3/8. As long as our scale is consistent, that's fine. 4/8. And I'm going to just move this over a little bit. So I'm going to make it 2 bars. So 0, 1, 2, 3. Again, how you do the bars is up to you, but the main thing is that they need to be together. They need to be touching. There's no gap. And we'll talk a bit more about that later in a further unit. But for right now, again, remember histogram shows that there's no gaps between. So for 0, we have 1/8 probability. There's a 1/8 probability that we're having 0. There'd be a 3/8 that we're having 1, as well as 3/8 that we're having 2. So that is what the middle would look like. And then it is 1/8 for having, or probability for having 3 girls. So again, probability is on the Y. We didn't really do this on the last one, but number of girls or the different outcomes of the random variable is on the bottom. Now we want to calculate the expectation for the number of girls in a family of 3 children. So we want to figure out what is the expected value. How many girls would we expect the family of 3 children to have based on the probability? So the probability, how we calculate that, again, the expected value, so E capital X is equal to the sum of X times PX, or each outcome multiplied by its probability. So 0 times 1/8 plus the next outcome, 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. And when we go through and we add all this up, multiply and add them all up, we should get that we'll have roughly 1.5. So the expected number of girls that this family of 3 children will have is 1.5. Now, obviously, that doesn't quite make sense. How can you have half a girl, right, or half a child? It doesn't really make sense. But that's okay because that's our expected value, right? We're basically finding a weighted average. We're finding an average. So although 1.5 doesn't make sense, it works when we're doing the expected value. So it's okay to have a decimal. The last one, a lottery has a $10 million grand prize, a $500,000 second prize, and 10 $50,000 third prizes. A ticket costs $5 and 4 million tickets were sold. How much can a participant expect to win? So here we need to find our expected value or the weighted average. So we need to kind of put this into a table first because we need to look at the different outcomes. So the different number of outcomes are X. We're going to look at the different number of winnings. So I could have the grand prize. Let me move this over a little bit. So I could have the grand prize, the $10 million. I could also have second prize, which is $500,000. I could also have then $50,000 for third prize. And I could also win nothing, right? Remember, the probability distribution looks at all the possible outcomes. So we could win any of those prizes as well as nothing. Now, in order to calculate the expected value, again, remember that is the sum of expected value is equal to the sum of each outcome multiplied by its probability. So we need to calculate the probability of each outcome. So in this case, for 10 million, there is one 10 million prize out of 4 million possible tickets. Because again, there's 4 million tickets, only one of them is going to win the grand prize. I'm just moving this down to make a little bit more room. Second prize, again, there's only one of them out of the 4 million. So 1 out of 4 million. For the second or the third prize, the $50,000. So again, we'll just highlight kind of where this is coming from. There are 10 tickets or 10 prizes of 50,000. So that would be 10 out of 4 million. And then lastly, to win 0 or win nothing, well, there's 4 million tickets minus the 1 grand prize, minus the 1 second prize, minus the 10 third prizes, which leaves us with 3,999,988 out of 4 million. So that's the probability of each outcome. Now what we want to do is we want to take each outcome and multiply it by the probability. So you could do this in the table. You could just directly do this in the formula. Either way works. I'm just going to put it into a table because it's going to be a little bit easier to organize. So 10 million times the probability, which is 1 divided by 4 million. We're left with 2.5. 500,000 times 1 divided by 4 million, right, because of the probability. we get 0.125. 50,000 times 10 divided by 4 million is 0.125 again. And then 0, the number of winnings times anything, is 0. So when we add them all up, so then our sum, 2.5 plus 0.125 plus 0.125 plus 0 works out to $2.75. So that means that the expected value, or the expected amount that we would expect to win per ticket, is $2.75. So expect to win $2.75 per ticket. Now, what else could we say though about this? Well, the other piece of information is that a ticket costs $5. So if we're spending $5 a ticket, but we're only expected to win $2.75, then that means that we're really going to, every time we buy a ticket, we're basically losing $2.25. Basically, the value that we're paying is more than what the value of the ticket is based on the prizes. So we expect to win $2.75. And then again, we could do another therefore statement. Therefore, at $5 a ticket, we can expect to lose $2.25 per ticket. So would it be worthwhile to play this lottery? Chances are no, because every time we buy a ticket, we're basically losing money. Even if we did win in the long run, chances are we are probably going to be losing money by the time that we get there based on the expected value. And you can see that in the probability of the different outcomes, right? It's highly more probable that we're going to lose than win. So each ticket technically has a losing value or a negative value. So that's a brief overview of probability distributions. Again, it's a list of all the possible outcomes and the probability attached to each outcome. We also looked at the introduction of expected value, which is what we would expect to happen or expect to get in a given scenario. The future lessons are going to look at specific scenarios of this and with specific characteristics and specific formulas to help us calculate the probabilities. But again, this is just an overview to help us lead into the next stuff.